It's a pleasure to be here in Korea speaking. Everything I'm going to talk about today is joint work with Erhard Nair and Prasad Sanesi, and the slides that I'm using are available on my webpage if anyone's interested, and the full details are available in a preprint on the archive. So let me start off by giving you an overview of what I want to say today. So the goal of this work and this talk is to classify the irreducible finite dimensional representations of a certain class of Lie algebras. So I'll start off by telling you what that class of Lie algebras is that we're interested in. They're called equivariant map algebras. And then I'll give you a bunch of examples of equivariant map algebras to give some motivation for why this is an important class of Lie algebras. And then I'll start giving you the results on the classification theorem. So the important ingredient, the main ingredient in the classification theorem is the notion of an evaluation representation. So I'll start off by telling you what an evaluation representation is and how we can parameterize all the evaluation representations. And then I'll tell you this classification theorem, how we can describe all of these finite dimensional irreducible representations. And then I'll return back to these examples and tell you what this classification theorem says in those specific cases, how we get a description of all of these representations. So we'll see in some cases, in some of these examples, a classification was already known, so we recovered this classification, but in sometimes a sort of a simplified way of describing these representations. But in some cases, a classification wasn't known, so we get a new classification of these finite dimensional irreducible representations. So all of the representations really that I'm interested in for this talk are irreducible finite dimensional. I don't want to keep saying this phrase over and over again, so I'll use the word small to mean finite dimensional irreducible representation. Okay, so let's start off with the description of what these equivariant map algebras are. So first of all, I'll omit the word equivariant and I'll just describe map algebras. So all they are is the following. We pick some field, algebraically closed of characteristic 0. We have a scheme over this field, or you could just think of an algebraic variety if you're not so familiar with schemes. Most of the examples that I'm going to give today are actually where X is a variety. Gamma will be the coordinate ring of this variety or this scheme, and little g will be some finite dimensional Lie algebra over K. So a lot of the examples it'll be a simple Lie algebra or semi-simple Lie algebra, but it can really be any finite dimensional Lie algebra. So the map algebra, or the untwisted map algebra, is just the Lie algebra of regular maps from this variety or this scheme to our Lie algebra. And we have pointwise multiplication. So that's a map algebra. So that's sort of a geometric way of thinking about it. You can also think about it in a more algebraic way, that this map algebra is just G tensor this coordinate ring. And so in Vajanthi's talk, she discussed G tensor A, these types of Lie algebras, and this is essentially the same type of description, right? Just G tensor some coordinate ring. So let's give some examples before we add in the word equivariant. Let's give a few examples. If X is discrete, then this map algebra is just isomorphic to some copies of G, because we just take one of these maps and we evaluate it at all the points, and then this gives us this isomorphism. So this will be an important example for what we're talking about, because this type of isomorphism is how we're going to get what are called evaluation representations. So in particular, if your variety is just a point, then your equivariant map algebra is just isomorphic to G, because all that we have is the value at this point. And we call these types of maps evaluation maps. We're evaluating at these points. So another example of map algebras are the current algebras. So if you take your variety to be just k to the n, in other words, the coordinate ring is just polynomials in n variables, then this is called the current algebra. So your map algebra is just G tensor this polynomial ring, and this is an example of a map algebra. Another example are the multiloop algebras, or the untwisted multiloop algebras. Here your variety is k star to the n, so your coordinate ring is Laurent polynomials in n variables, and so your map algebra is just G tensor this ring, and this is an untwisted multiloop algebra. When n is equal to 1, this is called the untwisted loop algebra, and it plays an important role in the theory of affine Lie algebras. I'll say a little bit more about that when we add in the twisting. One more example, so-called three-point Lie algebras. So the three-point Lie algebras are just another case of these map algebras. you take your field and remove 2 points, say 0 and 1, which is the same as taking P1 and removing 0, 1, infinity. This is why they're called 3-point Lie algebras. Then your coordinate ring is just polynomials in T, T inverse, and T minus 1 inverse. And you form this equivariant map algebra, and this is called the 3-point SL2 loop algebra. So some remarks about this example. Removing any 2 points from your field gives you an isomorphic map algebra. So really it only depends on how many points you're removing. And this Lie algebra that you form in this way is isomorphic to what's called the tetrahedron Lie algebra. So that's an example of these map algebras. And it splits into a sum of 3 copies of what's called the Onsager algebra, which I'll describe in more detail a little bit later. So we have lots of examples of these map algebras. This is some general construction that generalizes a lot of Lie algebras that people study for various reasons. So now we want to add in a group action to get the notion of an equivariant map algebra. So we have some finite group, and we'll suppose that this group acts on both our scheme, or our variety, and the Lie algebra by automorphisms of the two. And then an equivariant map algebra is just, well, it's the subalgebra of the map algebra that consists of equivariant maps, maps that commute with this action of the group. So at this point, I should note, of course, if you take any scheme or variety, then this equivariant map algebra, because we're looking at globally defined maps, is exactly the same as the equivariant map algebra where you replace your scheme by the spec of the coordinate ring. So the reason I make this note is because of this remark, we can always assume that our scheme is affine. And so in the statement of our classification theorem, it will be stated for an affine scheme. But because of this remark, it really applies to all schemes. Right? We can just always reduce to the affine case. Okay, so this is an equivariant map algebra. It's just equivariant maps from some scheme or variety to some finite dimensional Lie algebra. Now, if we want to give an algebraic description of this, again, it's just, remember our map algebra, the algebraic description was this finite dimensional Lie algebra G tensor some ring. And so the equivariant one, we just have a group action. So if we have our group action on the scheme, then we have a group action on its coordinate ring. Right? It just acts G times F at some point X is just F of G inverse X. This is the usual action on the coordinate ring of a variety or a scheme. And so then G acts diagonally on this algebraic description of the map algebra. And the equivariant map algebra is just the G invariance under this diagonal action on this G tensor, this ring. So this is just an algebraic description of the same object. So let's give some examples of these equivariant map algebras. So first of all, if the group acts trivially on just the Lie algebra, G, then this equivariant map algebra is just a normal map algebra on the quotient of X by G. And what I mean by the quotient is precisely the spec of the G invariance of the coordinate ring. Right? So if G acts trivially on our Lie algebra, this just reduces essentially to the case before where we have no group. So let's get a more interesting example. So multiloop algebras. So now we take our group to be some finite abelian group, say Zm1 through Zmn, and we take our variety to be k star to the n. So now we want some action of the group on this variety. So there's a natural way to get an action of the group on this variety. We pick some roots of unity, some mi roots of unity, and then the group acts on the variety just by multiplying the coordinates by appropriate powers of this root of unity. Right? So this gives an action of the group on this variety. And then we won't need an action of the group on the Lie algebra as well. Well, that's just the same as giving n commuting automorphisms of this Lie algebra, such that if you raise this sigma I to the mi, you get the identity. Right? This is equivalent to specifying an action of the group, this group G on your Lie algebra. So then you can consider this twisted multiloop algebra. We have the action on the variety on our little Lie algebra G. We consider the space of equivariant maps, and this is called a multiloop algebra. Or if we want to emphasize the fact that there's a group action here, it's a twisted multiloop algebra. And if n is equal to 1, this is called the loop algebra. So as I mentioned before we had the case of twisting, this is related to the theory of affine Lie algebras, these loop algebras. So the affine Lie algebras can always be constructed from these loop algebras. So we take one of these twisted loop algebras, we take a central extension, and then add a derivation. And we can construct all of the affine Lie algebras in this way. You can explicitly write down what the Lie bracket is, but we won't use this, so I won't write down these formulas. But these play this important role, and it's one reason people study these loop algebras, because of their role in the theory of affine Lie algebras. So that's one special case of equivariant map algebras. Another is called a generalized Onsager algebra. So here our group is just Z2, our variety is just K star, and G is any simple Lie algebra. So then we have a group action on the variety just by taking X to X inverse. We can have G act on our Lie algebra by any involution we want. And in a special case, when it acts by the Chevalley involution, we'll call this O of G. So the reason this is called a generalized Onsager algebra is because what's usually called the Onsager algebras is just a special case of this. So if our field is the complex numbers, we take the Chevalley involution, and our little g is SL2. This is isomorphic to what's called the Onsager algebra, which was played an important role in Onsager's solution of the 2D Ising model. So this is an algebra people have studied. And then this was extended by Ugloff and Ivanov to the case of SLN. Again, your group is acting by the Chevalley involution, but now you replace SL2 by SLN, and they study various properties of this Lie algebra. Okay, so these are some examples of equivariant map algebras. Now we want to, remember, classify these small representations, the finite dimensional irreducible representations. And a key element of the classification theorem is the notion of an evaluation representation. So remember, evaluation we discussed before. So evaluation is just we pick some n-tuple of points in our variety or our scheme, and then we take the elements of our equivariant map algebra, and we just evaluate at these points. Right? So we get a map from the equivariant map algebra to the n-fold sum of this little Lie algebra G. And what's important for us is to know the image of this map when we want to discuss these representations. So in general, this is not a surjective map. Right? And the reason it's not surjective is the following. So for any point, we can consider the stabilizer of that point. Right? So we consider the subgroup of our big group that's acting that fixes this point. And then we can take this subalgebra of our little Lie algebra that's fixed by the stabilizer of that point. Okay, so for every point, we have the stabilizer and this fixed point algebra that's fixed by the stabilizer of that point. And then we can describe what the image of this is. So if we pick an n-tuple of points, no two of which lie in the same orbit, then the image of this map is precisely the sum of these fixed point Lie algebras. All right, so this evaluation map surjects onto this. I mean, it's easy to, the inclusion is obvious. The image of your map at a point that's fixed by some group has to lie in the part of the Lie algebra that's fixed by that group, just by the equivariance. And then the other inclusion isn't so hard to see. So this is surjective. So evaluation representations we think of in the following way. So we have some variety or some scheme X, and we have an n-tuple of points on this variety or this scheme. So then for each point, we want to fix a representation. And we fix a representation of the fixed point Lie algebra that corresponds to that point. So we have n of these representations. And then the evaluation representation is just, well, we take our equivariant map algebra, we evaluate at these points, that lands in here, remember, and then we take the corresponding representation, the tensor product of these representations that we have for each point. This is a representation of this sum. And so we get a representation on the tensor product of these vector spaces. Right? So this is an evaluation representation. We have a bunch of points, we evaluate, and we have representations at each point, and so we take the corresponding representation of this direct sum of Lie algebras. So a couple of remarks about this definition. So this differs from the classical definition of evaluation representation in a few important ways. So the one is a little bit minor. Sometimes people use the term evaluation representation just for a single point, and they would call what we have here as a tensor product of evaluation representations. But for us, evaluation, we can have a bunch of points, and this tensor product we just call evaluation representation. So that's sort of minor. The important difference between this definition and the more classical definition of evaluation representation is that at each point, we're putting a representation of this fixed point Lie algebra, Gx. Whereas classically, you put a representation of the full Lie algebra, G. So if Gx freely, then all of these Gx's are equal to G, and so this is the usual definition. But in general, if you have points that have non-trivial stabilizer, this is a different definition. It's more general. I mean, the reason it's more general is because, yep.
Before you were talking about the x's being, none of them being in the same G orbit.
Right.
In your definition of evaluation representation, you don't have that restriction?
No, we don't have that restriction. The classification theorem will have that back in it. But you can define evaluation for any number of points you want. It's just if they align the same orbit, you won't get an irreducible representation, is the thing. But in the definition, there's no reason to assume it. So, right, so the reason this is a generalization of the classical definition of evaluation representation is really this key idea, right? That if a point has non-trivial stabilizer, then the Lie algebra fixed by that stabilizer could be a proper subalgebra of G. And so not all representations of Gx extend to representations of G. So we have more choice in what representations we can put at these points in this definition. We also don't require these representations to be faithful, which is sometimes required in the literature. So the reason we want this definition, this more general definition, is we'll see that it gives a more uniform classification of irreducible representations. We'll give an example of that later. So we'll see cases where in the classical definition there will be representations that are not evaluation representations, but in this definition they are evaluation representations. So it sort of encompasses a greater class of representations. Okay, so our first goal now is to parameterize evaluation representations. So we do that in the following way. Right? So at each point of our variety or our scheme, x, we can take our x to be the isomorphism classes of small representations of that fixed point Lie algebra that we think of as living at that point. And then R of big X will be the disjoint union of all of these sets. So now we want some G action on this set of isomorphism classes. So there's a natural G action because it's just some trivial exercise to show that the stabilizer of the point G times X is just the conjugate of the stabilizer Gx. And so G times this fixed point Lie algebra, G upper X is G upper Gx. And so we have an action of the group on this collection of isomorphism classes. Right? If we have the isomorphism class of some representation rho, then we act on it by G, and this is the representation rho composed with G inverse, and that lies inside Rgx. So we have the action of the group on this set of isomorphism classes. And so then our key set that's going to parameterize the evaluation representations is the following. So we'll call it F, and it's the set of all functions from our variety or our scheme to this set of representations of the fixed point Lie algebra that satisfy the following properties. They should be G equivariant maps. At any point x, we should associate a representation of the fixed point Lie algebra Gx, and the support should be finite. Right? So this is the key parameterizing set that's going to parameterize evaluation representations. So just let me draw a picture for you of how you should think of these functions. So say this is our variety or this is our scheme. You should think of this parameterizing set or elements of this as assigning to a finite number of points of your variety or your scheme representations in a G equivariant way. Right? So if the point x we associate the representation rho, then at Gx we have to associate the representation G rho, etc. So we have this G equivariant map from our variety or our scheme to this collection of representations. At each point x we're putting a representation of this fixed point Lie algebra Gx. Okay, so to each of these functions we can associate an evaluation representation. So if we have one of these functions, then we pick an entiple of points that has one point in each orbit of the support. The support will be some finite number of orbits. And so to a function, we associate this tensor product. Right? We pick one point from each orbit. We take the corresponding evaluation representation. Really, it's an isomorphism class of an evaluation representation. And we take this tensor product. And this isomorphism class is independent of which point we pick in each orbit. So it doesn't really matter which one we pick. And if our function lies in this set F, then this is the isomorphism class of a small representation of our equivariant map algebra. So here we're using the fact that we only no 2 points lie in the same orbit. Right? So we use that fact to know that we get an irreducible representation. And the first thing is that this is an injective map. So if you have two different functions, you take the corresponding evaluation representation, then you get different evaluation representations. Right? So this map is injective. And this parameterizes all of the evaluation representations. Okay, so that's evaluation representations, but before we can give the classification theorem, it's not quite enough to know the evaluation representations, because we also need to know about the one-dimensional representations of our Lie algebra. So one-dimensional representations are in some ways sort of simple. Any one-dimensional representation is just a linear map from the Lie algebra to the field, the ground field, that vanishes on the commutator. This is a one-dimensional representation. So we can identify one-dimensional representations with elements of the dual of the Lie algebra modulo its commutator. And two one-dimensional representations are isomorphic if and only if they're equal as elements of this dual space. So this dual space parameterizes all the one-dimensional representations. Okay, so now we can give our classification theorem of all the small representations of equivariant map algebras. So we have our setup. G is a finite group. It acts on some affine scheme, but remember this affine is really not a restriction because we can always reduce to the affine case. And some finite dimensional Lie algebra. We have our equivariant map algebra, and now we can parameterize all of the small representations. So if we have a pair, an element of this dual space, and one of these functions, we can associate the tensor product of that one-dimensional representation and the evaluation representation. And this is a surjection from this product to the isomorphism classes of small representations. So all small representations are of the form a one-dimensional representation times an evaluation representation. Okay? So this is sort of the main result, that we get all these small representations in this way. A few remarks. So this is our map. It's not injective in general because it's possible to have evaluation representations that are non-trivial and are one-dimensional. And the way that this can happen is because it's possible for these fixed point subalgebras to not be perfect. So remember, perfect means the Lie algebra is equal to its commutator. So for example, they can be reductive but not semi-simple. Even if G is semi-simple, these fixed point Lie algebras can be non-semi-simple. So a simple example of that is if we took our Lie algebra to be SL2, our group to be Z2, and our variety just to be C, then we could have G act on the Lie algebra by the Chevalley involution. We can have it act on the variety by multiplication by -1. And then, so the point 0 is fixed by this action. Right? So if you look at this fixed point Lie algebra associated to 0, that's just the fixed point algebra of G. And this is one-dimensional because the Lie algebra subalgebra fixed by the Chevalley involution is one-dimensional. And one-dimensional algebras have lots of non-trivial one-dimensional representations. So we can have evaluation representations associated to the point 0 that are non-trivial and one-dimensional. And so that makes this map not injective because we could also think of that as coming from some lambda. But we can specify precisely when two of these are isomorphic. So we really do get a classification because we can take care of the fact that this is not injective by really describing when two are isomorphic. And if you restrict this map to either factor, this is an injective map. Okay, so a corollary that we'll use in some of our examples is, well, if M is perfect, so if M is equal, remember M is this equivariant map algebra, if it's equal to its commutator, then this factor vanishes. And so all of the all the small representations are evaluation representations, and they're just parameterized by this set F. So for instance, this condition we'll use in some of our examples, if the fixed point Lie algebra, its product with the Lie algebra gives you the full Lie algebra G, then this equivariant map algebra is perfect, and all the small representations are evaluation representations. In particular, one type of group action on Lie algebras that people often consider is acting by Dynkin diagram automorphisms on the Lie algebra. And in that case, this condition is satisfied. And so all the small representations are evaluation representations if your group acts by Dynkin diagram automorphisms. So being perfect is a sufficient condition for all the small representations to be evaluation representations. But we'll see it's not a necessary condition. It's possible for your equivariant map algebra to not be perfect, but still have all the small representations be evaluation representations. Okay, so now we have our classification theorem. Let's go back to some of the examples that we had of equivariant map algebras and see what this classification theorem tells us for these examples. So the first is untwisted map algebras. So if our group is trivial, then our equivariant map algebra is just the same as the normal map algebra. Our fixed point Lie algebra is just our whole Lie algebra. And so if the little g, this finite dimensional Lie algebra, is perfect, then this condition in our corollary is satisfied. And so all of the small representations are evaluation representations. Right? So we saw this result also in Vajayanthi's talk. She said this result that all the finite dimensional irreducible representations, when you didn't have a group action, were tensor products of evaluation representations. This is just the same result that we're seeing here. So now remember, multiloop algebras were an example of the equivariant map algebras. So if we have a twisted multiloop algebra, it turns out you can show that this is a perfect Lie algebra, this equivariant map algebra. And so all the small representations are evaluation representations, and we have this classification of all the small representations by this set F. So this classification was known already in a different form. I mean, so what we recover here is some results of Chari and Presley for loop algebras, and more recently of Batra and Lau for multi-loop algebras. But our description is slightly different. Right? So the description given before is usually, the method was to prove that everything is an evaluation representation, all the irreducible finite dimensional ones, and then give some description of when two evaluation representations are isomorphic or not. So here we get this enumeration, this classification by these finitely supported equivariant functions. So it's a slightly different description, but we obtain the same classification. And this description in terms of these finitely supported equivariant functions is, I think, a little bit more simple and more uniform than some of the conditions that appeared in previous classifications. There were conditions in some cases for, say, the multi-loop algebras that don't appear in this description. We just have these finitely supported equivariant functions, this sort of uniform description. And in this case, I mean, things are a little bit simple from our point of view in the sense that the action of the group on this variety or this scheme is free. And so all of these fixed point Lie algebras, since no points have any non-trivial stabilizer, they're all our full Lie algebra. So since these two are always the same, this more general notion of evaluation representation is really not playing a role here. All right? So these are just the same notion of evaluation representation as people usually consider. So what about this generalized Onsager algebra? So here our group, remember, was Z2. Our variety was K star, and G was a simple Lie algebra. And the group acted on the variety by taking X to X inverse. And we could act on our Lie algebra G by any involution we wanted. So it turns out that in this case, again, all the small representations are evaluation representations. And we get this enumeration of all these finite dimensional irreducible representations by these finitely supported equivariant functions. But this description is slightly different from what we saw in the multi-loop algebras because the more general notion of evaluation representation can play a role. So let me give an example. So in this generalized Onsager algebra, there's two different types of points in our variety because remember our action took X to X inverse, so there are some fixed points. If X is equal to plus or minus 1, then these points are fixed by the action of G. Right? So then our stabilizer is the full group Z2, and these fixed point Lie algebras are the part of your Lie algebra that's fixed by the group, and the group member can act by any involution. Whereas if your point is not plus or minus 1, then the group acts with trivial stabilizer, and Gx is equal to G. So even if, remember, G is simple in this example, but if you take a group action on a simple Lie algebra, then in general all you know is that the fixed point Lie algebra is reductive. It may not be simple or even semi-simple anymore. So this fixed point Lie algebra can be semi-simple, or it can have a one-dimensional center. It can be reductive with a one-dimensional center. So when it has a one-dimensional center, then this generalized Onsager algebra is not perfect anymore. And the reason it's not perfect is we can place one-dimensional non-trivial representations at these points plus or minus 1, where we have these one-dimensional fixed-point algebras. But under this more general definition of an evaluation representation, it's still the case that all the small representations are evaluation representations, because we're allowed to put representations of gx rather than g at these points. But under the classical notion of evaluation representation, there are small representations which are not evaluation representations. So this is sort of one of the motivations for this more general definition, that this more general definition allows us to say that these are all evaluation representations, whereas under the more classical definition, it's not the case. So remember, this was the generalized Onsager algebra because a special case of it was the Onsager algebra. Right? When our field is C and our Lie algebra is SL2 and the action is the Chevalier involution, this was the Onsager algebra. And so this is one of these examples where this fixed point Lie algebra is one-dimensional, abelian, and so this Lie algebra is not perfect, the Onsager algebra. Now these small representations of the Onsager algebra were previously classified by Date and Rohn, but they used the classical definition of an evaluation representation, and so not all of the small representations were evaluation representation. So to get around this, they had introduced the notion of the type of a representation. So type 0,0 representations were evaluation representations, and then all other types they could reduce to the 0,0 case by some automorphism of the enveloping algebra. So they approached the classification from that way. And for the other cases, the more general setting, this classification seems to be new. So we obtain a classification of all the small representations of these generalized Onsager algebras. So most of the examples I've given so far were non-abelian examples, or were examples where the group was abelian. So let me give you an example where our group is not abelian. So let's take our group to be S3, the symmetric group on 3 letters. And let's take our variety to be P1 minus 3 points, and G to be SO8, so the Lie algebra of type D4. So here's our Dynkin diagram. Well, the symmetry group of this Dynkin diagram is S3. Right? We can permute any of these 3 vertices out here in any way we want. So we have a natural action of the group on this Lie algebra by Dynkin diagram automorphisms. Now we also want an action of the group on our variety. Right? So now we have to remember that a homography of P1 is determined by where it sends any 3 points. And you can send any 3 points anywhere you want by a homography of P1. So if we take P1 and we want an automorphism of P1 minus 3 points, we can think of a homography of P1 that permutes these 3 points. Right? And for any permutation of this set, 0, 1, infinity, there's a unique homography of P1 inducing that permutation. So we have an action of S3 on P1 minus 3 points in this way. So we have our group acting on the variety and on a Lie algebra, and we can form the equivariant map algebra now. So we take this equivariant map algebra, and you can show that it's perfect. It's not so hard to show. We just use this corollary that we had. So then our classification tells us that all the small representations of this equivariant map algebra are evaluation representations, and it enumerates them. We have a bijection between all the small representations and this set F of finitely supported equivariant maps. Well, we want to describe these a bit better. I mean, what do these maps F look like? Well, so remember, these are maps from the variety to the isomorphism classes of these fixed point Lie algebras. So we need to know what the stabilizers of the points are under this action. So it's just a little bit of linear algebra. You can compute what all these stabilizer groups are, and this is what you get. So you have a bunch of points. I mean, most of the points have trivial stabilizer, and these are the points that have non-trivial stabilizer. So you have 3 points whose stabilizer is isomorphic to Z2, and then the fixed point Lie algebra is isomorphic to B3. So it just comes from taking this Dynkin diagram of type D4. You have this automorphism that flips 2 nodes, and then the fixed point Lie algebra is isomorphic to B3. This is this well-known folding of Dynkin diagrams. And then we have 2 points whose stabilizer is isomorphic to Z3, and then the fixed point Lie algebra is G2. So we take this Dynkin diagram of type D4, We have this automorphism of order 3. This folding gives us G2. And these points are grouped, of course, into orbits. So these 3 points form an orbit of size 3, of course, since the stabilizer has size 2. These 2 points also form an orbit. Right? So we have these 2 special orbits. All the other orbits have 6 elements, and the group acts freely. So our elements of F are maps from our variety to points, where at each point they associate a representation of this fixed point Lie algebra. So to the 3-element orbit, they can assign irreducible representations of type B3. To this 2-element orbit, they can associate irreducible representations of type G2. And to all the other points, they can associate representations of type D4. Right? So we think of we sort of think of this picture. Here's our P1 minus our 3 points. We've got this orbit of size 3, where we can associate representations of type B3. We've got these 2 points where we can associate representations of type G2. Remember, this association has to be equivariant. So once we know the representation at one point, we know at all the other points on the orbit. And then at all the other points, which come together in orbits of size 6, we put representations of type G4. Right? And these are all of the finite dimensional irreducible representations of this Lie algebra come from these type of evaluation representations. But we see we get some sort of interesting phenomenon. I mean, we get the representations of type D4, B3, and G2 all appearing in the representation theory of this one Lie algebra. So let me finish off with saying some further directions of this work. So, I mean, what we've done is we've classified these finite dimensional irreducible representations. But that's not enough, because this category of finite dimensional representations is not semi-simple. And so there are indecomposable representations that are not irreducible. And so there's still a lot more work to do if you want to describe this whole category. So the next step is, can you describe all the finite dimensional irreducible representations? All the finite dimensional representations that are not necessarily irreducible. So this is related to what Vaijayanthi talked about this morning, talking about maybe come up with some notion of a twisted vowel module. She was talking about this situation where there's no group action and describing these vowel modules. Can we add in some group action and get a twisted version of these? Can you give a block decomposition of this category? Then the other next step is to think about the fact that what we discussed here, these equivariant map algebras, remember, are globally defined functions from this variety or this scheme to your finite dimensional Lie algebra. So it's natural to think about, instead of globally defined functions, to think about sheaves of functions. So you could have G-equivariant sheaves on your scheme or on your variety with values in the Lie algebra. And then this work would just be sort of taking the global sections of these sheaves and be the global version of some maybe deeper theory where you can replace global things by sheaves, which would be just locally defined. All right, so I'll stop there.